Do you see, can you see my slides?
Yes.
Okay. First of all, I would like to thank Professor Casanova for inviting us and for providing this great opportunity of presenting our works to the faculty and to the students of PUC. As Professor Casanova introduced, I am Raffaele Perego. I'm Research Director in Pisa, in CNR. CNR is the largest public research institution in Italy that is not a university. We have a mission that is similar to that of a university, but we do not have teaching duties. And we have to perform research to promote the internationalization of the national research system and support innovation of in the competitiveness of the Italian system, even with a connection with industries. CNR is organized in several research areas and institutes, thematic institutes. It covers all the fields of knowledge. And in Pisa, there is a very large campus with hosts 13 institutes, including computational science, computational linguistics, medicine, physics, neurobiology, and so on and so far, with more than almost 2,000 people. And my institute is the Institute of Scienza, Tecnologie, dell'Informazione that perform research on various areas of computer science, including also application and technological transfer to industries. Okay, I lead a research group that is that includes about 20 researchers, including also Chiara Renzo, that will introduce her work the next week. And we perform in our lab research on the following 4 areas mainly. Even this is, of course, is not an exhaustive list. We work on information retrieval. I personally work mostly on information retrieval and efficient AI for information retrieval. Our focus is on very often on high performance and finding solutions that are both efficient and effective and can use a limited amount of computational resources to solve the problem we address. For that tasks, we use distributed system, of course, including the GPUs, and we are interested also on the technical issues that the use of this kind of infrastructure provide. The other research area that is covered by our lab is the analysis and the semantic extraction and mobility spatiotemporal data that is a task, a research line that is led by Chiara that will talk next week. Okay, what I'm going to present here are the research, the result of 2 works that I presented recently in July at SIGIR 2024. It is the conference, the most important conference on information retrieval worldwide. And I'll present 2 works. One of these, the first that I will going to present, is strictly related to the course you are attending about generative AI. The other one is somehow related in the sense that deals with making more effective the system that use encode learned representation in latent spaces obtained with a deep learning architecture. Of course, I know that these topics are maybe partially outside of your knowledge, and so do not hesitate to interrupt me and ask questions if something is not clear, or if you need further discussion about some of this. Indeed, I started with this work that regarding how we can improve retrieval augmented generation systems by using sentence clustering and reordering. This is the part of the talk which most deal with generative AI, as you will see. Before starting to discussing the contribution of the work, I will give a very, very short introduction of information retrieval and discuss how information retrieval moved from classic information retrieval to the use of LLM and the pre-trained language model on which the more advanced information retrieval techniques are based on now today. Okay, as you probably know, the classical information retrieval was mostly based on the concept of lexical matching, in the sense that information retrieval addresses the task of retrieving from a collection of documents, in the case of textual documents, information that is relevant for a user query. And so we assume that the user submit to the information retrieval system a query, in our case, a textual query, and the system is able to find in a large collection of documents in a very short time the set of documents ranked by their expected relevance that are that contains possibly the answer to the query submitted by the user. In the case of classical information retrieval, the matching between the query and the documents in the collection were principally made by using, of course, an inverted index that allows us to make the search of document efficient. And the inverted index is simply a set of a vocabulary of all the terms that are included in the document, and a list of, for each terms in the vocabulary, of all the documents that contain the given term. The indexing of the collection in an inverted index allows to answer very efficiently queries where the user specifies a set of terms that are searched for in the collection of documents, and the documents are sorted by their expected relevance on the basis of some scoring model. One of the most famous and most popular scoring model that belongs to classic information retrieval is the one that is shown in this slide, that due to Robertson, and that is called BM25, that is based on a sound principle of probabilistic relevance principle. This BM25 is still used, but just starting from the 90s, the community, the information retrieval community, started to use machine learning to improve the ranking and the effectiveness of the system, and improve the way in which the documents are ranked with respect to the user need as indicated in the query. This development was very important for the case of web search, where we have, of course, some textual content in the document, but we have also a lot of metadata information that are relevant for identifying the pages that are trustful and relevant. And so we do not use only the content of the page to rank these pages on the basis of the user query, but we use also some other information which comes from, for example, for the structure of the web. And we can assume that the pages that are linked by more link in the web network are more relevant and more important than the ones that do not have any in link to the page. And to use this information, the community developed a set of tools that goes under the name of learning to rank, and that allow to learn from supervised data set, possibly large supervised data set, a ranking function that allows us to order the set of documents on the basis not only of the context, the textual content of the document, but also on the basis of the estimated importance of the page for the user that submitted the query. Then, as in many fields of computer science, including all the NLP application, there was the advent of a deep neural network, and in particular, in the case of information retrieval and natural language processing, the introduction of transformer models with the famous paper about attention is all you need from 2017. In this case, following this work, the information retrieval community start to focus on the use of a pre-trained language model to improve the understanding of text in the query and in the document, and enhance the effectiveness and the quality of the retrieved documents in response to a user query. The first solution that is still quite valid was substituting the part that were previously addressed by using learning to rank with a deep neural network model that is based on the pre-trained language model, for example, BERT. Maybe you know about BERT, and the model where the model is fine-tuned for the ranking task, and so we give an input to the model a query and a document, and the model is able to understand if the document is relevant to the query, and providing us a score that estimates the relevance of that document for the query. When we then sort all the documents that are relevant, that are extracted, for example, from an inverted index by using BM25, a very fast retrieval, and we sort these documents and return the top 10 documents, for example, in response to the user query in this way. This kind of solution improved a lot the quality and the effectiveness of the system, because as you know, large language model, pre-trained language model, are able to capture complex language pattern and meaning, and to understand somehow the semantic of the text. And so we improved the information retrieval, moving from what was based mainly on lexical matching problem, in the sense of finding the document that contains a list of keywords and try to sort this document on the basis of their expected relevance, to another model where we understand, we use a pre-trained language model that are able to understand the semantic and the pattern, and to adapt to diverse query, and with an improved understanding of both the information need in the query and the content of the document itself. Of course, this comes with a cost. This major effectiveness with semantic interpretation of document queries comes with a cost. And this kind of models require significant computational resources and a very large data set for training and fine-tuning. And so while the classical information retrieval was quite efficient and easy to tune, even for small collection, and in the absence of very large supervised data set, neural IR requires a very, very large data set for training and fine-tuning the models. And the cost of processing a query is very, very high with respect to the one to which we were used to with classical information retrieval. Here we have a plot that shows this difference and this problem. For example, we see in a plot on the x-axis we have the query latency, the amount of milliseconds that processing a query requires, and on the y-axis we have instead a measure of effectiveness, a measure of the quality of the result that are retrieved from the document collection. As you can see, we have on the BM25 that is very, very fast, but provide a limited effectiveness, and completely on the other side of the plot, on the topmost right side, we have BERT, that is a large, a pre-trained language model that is, however, very, very expensive. And so processing a query, a textual query by using a cross encoder based on BERT requires about 3 seconds and half using a GPU with respect to the few milliseconds of using an inverted index and the BM25. Of course, what we would like to have in our desiderata is having a system that can perform as BERT, but require a computational time, a query latency that is comparable to that provided by BM25. And this is indicated in the green cross on the plot. And so to try to solve, to address this request for a larger efficiency of information retrieval based on deep learning model that without sacrificing the potentiality of a large language model that allows us to understand the semantics of that is hidden in the query and in the content of the document, the research community developed what are called B encoders for end-to-end neural information retrieval. In this case, we do not exploit the self-attention mechanism of a cross-encoder, but we encode separately the documents and the query. And so we can index offline all the document collection, and at query time we have only to encode the query and compute the score on the basis of the representation that the model learned for the document and the query itself. In this case, the document and the query are represented as vector, and the score is computed as some kind of similarity measure about between vectors. So for example, Euclidean distance or cosine similarity or some typical similarity measure. In this case, the difficulty is posed on learning the latent space in which the documents and the query are represented, and this latent space try to grasp all the semantics that is hidden in the concept that are described in the document in the query. For example, if we have a concept, the concept of mouse that can belong to different context. In one case, we can think to mouse as the device that we use with a computer, or otherwise we can think to the mouse as the rodent, as the animal. Of course, in a traditional information retrieval, where we have only lexical matching, these two concepts are represented in the same way. Here, instead, we use semantic vector that allows us to represent the concept in a latent space, and the concept of mouse computer and the concept of mouse rodent are far away in this latent space. When we receive a query that deals with a mouse, for example, one query could be mousetrap or mouse arrow, the latent space allows us, and we encode the query in the same latent space, and it is likely, and our desiderata is that the query mouse arrow will be encoded in a way that is very close, in a vector that is very close to the concept of mouse computer. And instead, the query mousetrap will be encoded with a vector that is very close to the concept of mouse rodent. In this case, the retrieval of documents that are relevant for the query is performed by finding the vectors, the embeddings that are more closer to the one that is the query that represents the query. And so the retrieval becomes a search over vectors and not more over posting list, as it was happening in the case of classical information retrieval system based on inverted index. And so with the use of this B encoder model, we are able to get a very effective system that are also fast and allow us to solve end-to-end a query in an amount of time that is reasonable with respect to the cross-encoder we analyzed previously. And so there is also another step that the community is starting to do, and that is is of course motivated by the introduction of a large language model that allows us to provide an even deeper understanding of the text that is included in a query and in documents. And so we are trying to understand how we can use the state-of-the-art LLM model and the state-of-the-art IR system-based OB encoder to provide a completely new experience for searching. And in this case, we want to combine these two kinds of systems in a way that can grant us all the advantages of both worlds, in the sense that we will have IR task, we will use IR system based on the encoder that provide us some very important characteristics that are efficiency, the use of documents that are reputable and coming from known sources, and the possibility of updating the knowledge base very efficiently. From the other hand, we have LLM that provide us the ability of semantic matching and understanding which is the similarity between two texts, and the ability of understanding exactly the content and the context of a query and of a document, and allow us to provide a very easy interaction with natural language with the system. And so we can think that in our modern information retrieval system, we will have a complex system that deals with this following three steps, where both LLM and IR can work together. The first aspect is query interpretation. Of course, LLM can enhance the query by understanding the intent, the context, and all the different aspects that a query can have. From the other side, the IR can use the refined query that was enriched by the LLM to retrieve the most relevant documents from a large data set that provide our knowledge base. The second step is contextual retrieval, in the sense that we can use a IR system based on encoder to find documents or part of text that semantically match the query. And we can ask the LLM to rank these documents on the basis of the semantic relevance on which this document of the query match. At the end, we can also use the LLM to generate coherent and contextually appropriate responses using the documents that have been retrieved by the system from the knowledge base. And so this gave origin to what we call now retrieval augmented generation. That is a system, a retrieval system that uses generative AI for improving the interaction with the user. And so we have, in this kind of system, we have a query coming from the user. We have a retrieval system that we will try to analyze in the following, that extract from the knowledge base a set of passages that are possibly relevant for the query. And then we have a large language model that can interpret these passages and the content of the query to generate a response, a single response that can be very, very important and can answer exactly the query provided by the user. These systems are nowadays quite popular. They start to be popular if maybe you have used some of this system, for example, the one provided by Bing that try to include a similar pipeline in their search engine, or even if you use a Copilot by Microsoft, the Copilot works exactly with a similar pipeline, and the difference. And there is a lot of difference between extracted language model and this kind of system, in the sense that in this case, the knowledge on which the answer to the query is extracted is not included in the large language model during at the training time, but instead comes from an external knowledge base that can be updated over time and can be referred in the responses. So you do not have only the response to the answer to the query, but you can also have information on the source from which the knowledge in the response was extracted from. And so this is an example, a simple, very basic example for showing you the behavior of this kind of system. We have a query that is a very traditional query. What is the color of Napoleon horse? This query goes to a de-encoder retriever that extracts from a knowledge base a set of documents, of sentences that contains information that is expected to be relevant for answering the query. In this case, we have, in this simple example, we have 3 sentences. In the first sentence is chunk 1. We see that Napoleon Bonaparte's horse Marengo was renewed for its striking gray color, and blah, blah, blah. Then we have 2 other chunks that talk about Napoleon and horses, and maybe these 2 are not so relevant as the first one for answering the query. Then we have a large language model that receives in input a prompt, and in the prompt we say to the large language model, answer to the question of the user, what is the color of Napoleon's horse, based on the following information. And we include in the prompt the content of the documents that were retrieved from the knowledge base. The LLM understands the query and understands the document, the semantic of the passages of the sentences included in the prompt in chunk 1, 2, and 3, and elaborate and generate an answer to the query that is correct. In this case, of course, Napoleon's horse's color was gray. And this is how retrieval augmented generation works. And so these are the advantages of this kind of mechanisms. The accuracy, because we combine the strength of state-of-the-art retrieval system and state-of-the-art large language model for generate accurate responses. We have reduced the risk of hallucination because we do not rely on the knowledge that was provided to the LLM at the training time, but we provide the LLM itself with updated knowledge about the topic of the query. In this way, it is simple, very easily, it's automatic having a knowledge update, and so we do not have to retrain the model to integrate in it the updated knowledge about a new event or new information. And we rely again on the LLM for understanding the semantics and the contextual importance of the documents, and generate an appropriate response. We have also scalability in the sense that we can use the information in an external knowledge base coded by a B-encoder to reduce the computational overhead that is due with respect to the use of effect of cross-encoder that we saw before, and we use the LLM only for generating a response based on a few information which is provided. We do not have to rank all the documents, but we need only to take a few documents that are likely to provide the requested information. And then finally, we have an increased flexibility because it's easy to integrate the system to a different domain by simply changing the knowledge base and maybe understanding which is the best prompt for the system, for the system in that domain. Anyway, we have also challenges in the sense that not nothing comes for free, of course, and we have some problems that have to be addressed in order to build a retrieval augmented generation system that is both efficient and effective. And now in the following, we see which are the main challenges that are behind this topic, this kind of system, and we try to introduce how we dealt with some of these challenges in the paper that we are which we contribute in the last period. Okay, the first challenge I glad is that we need a IR system that provide high recall, in the sense that we want to provide to the LLM model relevant information for the query by solving the semantic gap and providing a very good understanding of the text included in the query and in the documents. This comes from almost from free if we use state-of-the-art B-encoder models that, as we surveyed before, are able to provide us an efficient way of retrieving documents on the basis of user queries by understanding the semantic of the query and of the document as pre-trained language model does. And in this case, we know that we use the vector representation for both the query and the document, and we extract this document by using KNN, for example, search over a collection of vectors. We already understand that this kind of system are effective and provide state-of-the-art performance on both in-domain and off-domain data set. We have also other challenge in the sense that we know from the literature that LLMs are not good at reading too many chunked documents, in the sense that we cannot provide to the LLM with a very, very long list of documents extracted from the information retrieval system and ask to the LLM to understand where the relevant information is within these documents. There are previous studies that allow us to estimate somehow the number of documents, of pieces of text that we have to provide to the LLM to enhance effectiveness, and this number changes on the basis of the kind of queries and of the model. But anyway, we can perform some experiment to fine tune if we have a supervised data set to fine tune this number, and typically this number is ranges from 5 to 20. The other challenge is that the user model that may be not suited to model LLM use of input, in the sense that we are using the information retrieval system that was designed and built for a human, and we know that a human is used to receive the result of a query as a ranked list of results, where the most relevant information is likely to be in the first document. Either the position on the document in a ranked list, either is the expected relevance of that document for answering this query. We are not sure that this is how LLM reasons, and so we have to understand if this holds. And some literature show us that this is somehow different, in the sense that in this work that is titled "Lost in the Middle," they perform a lot of experiment to understand where the position, if there is some bias in the use of the information provided to the LLM, in the sense that since we have to provide a list of documents, a list of sentences to the LLM, it is important to understand if the order in which we provide this document is important for the LLM or not. This experiment showed that indeed it is, in the sense that different from the human that focus their attention typically on the first documents of a list of documents, the LLM have a quite similar but different behavior, in the sense that their attention is focused on the first document, as in the case of the human, but also on the last part of the document, as you can see from this plot, where they try to shuffle the order in which the relevant information is provided to the LLM, and understand in which case the accuracy is improved. And the result of the experiment was that the accuracy was improved by inserting the relevant knowledge, the relevant information at the beginning of the list or at the end of the list. The part in the middle is instead less important. The LLM pose less focus on the middle part of the context, and this could be very important. Anyway, in this work, they started to understand if there is some positional bias in the LLM system, but they do not understand, they do not try to understand which is the best ordering of the information that is provided to the LLM to improve effectiveness. And this is what we try to do as a first contribution in our work. Another aspect that is a challenge is that we have to deal with a different granularity of the documents in the IR system and in the LLM, in the sense that very often the IR system indexes documents that are complex and large. Instead, the context of an LLM is restricted, and it works best at the level of single sentences. And so, even if the last advances of large language models show it does that, they can understand also very, very large context. In the last development of ChatGPT 4 and Llama 3, we have very, very large contexts that can be given in input to the LLM. However, one of the first this aspect can be easily solved by using standard NLP tools that provide us a possibility of resolving resolution and replacing pronouns, ultra-generic terms with sentences that are self-contained and clear. Sorry, I hear a noise. Should I go on? You can understand me? Or?
Furtado, você pode fechar o microfone, por favor? Okay.
Oh, okay. Thank you.
Thank you.
Thank you, Furtado. And so one of the steps that the RAG system has to perform is splitting the document in shorter sentences by resolving anaphoras and making coreferent resolution. Those are substituting pronouns with the actual subject that comes from a previous sentences, in order to make each sentence very independent and self-contained. And so what we asked to perform as our contribution, as how we can leverage the representation space properties to boost RAG system in a specific case, and the case is the one of a dialogue-based retrieval augmented generation system. We will explain very shortly what this means, that we understand that the B-encoders and the deep learning models learn a representation of the text in a latent space. And we know that this latent, from previous studies, that this latent space has some mathematical characteristics. And this will be also the subject of my second contribution of today. We will see later. But anyway, we want to understand, we see that the way in which the entities and the documents and the text is placed in this latent space by the deep learning model is not uniform, but concentrate on specific regions of this space where we have some sort of clustering of spatial clustering of information representation, where the information that relates one to the other are in a more denser space in this latent space. And so we want to see if this property can be used to improve the retrieval augmented generation system that deals with dialogues, in the sense that we do not consider a retrieval augmented generation system that answer a single query, but the one that provide a more richer experience to the user, where the user start a dialogue with the system, and the dialogue is multi-turn and try to better answer the user need by including different aspects and different sub information need that the user want to know. For example, this is an example of an interaction with the user, and we have 9 queries that are asked to the system, and these queries regard the energetic drinks, and the user start to drink if Red Bull is okay or is bad, and how much you can drink in a day, and if there is what is the energetic ingredient taurine, and if there are health effects, and so on so far. And and the system try to answer to this query by extracting the knowledge from a large knowledge base that is used with a retrieval augmented generation system as the one we have described before. What we want to understand if this information can exploit the locality, the spatial locality of the representation in the dense latent space. We know from a previous study that we have, if we consider the representation of the queries and the answer and the relevant answer to this query in each conversation, we can observe a sort of clustering effect. Here we have the representation of a two-dimensional world of 5 conversations in a publicly available dataset provided by Trek, and in the circle, in the colored circle, we have the utterance, the queries in a conversation, and represented with the same color with cross symbols. We have the documents that are assessed in the golden standard as relevant for answering this query. And if we plot, in this case in 2 dimensions, this relevant document and the queries, we see that there are clear clusters that identify each conversation, because each conversation try to understand and to get the knowledge and to solve information needs of the user, and these information needs are semantically related, and so are represented in the same sub-region of the latent space. And what we want to understand, if we can rely on the similarity among retrieving documents to improve the effectiveness of the RAG system, in the sense that we want to understand if we can cluster the answer that are extracted from the information retrieval system and order this answer on the basis of their similarity to provide a more structured context to the LLM to generate an effective response. And so to answer this query, we build this pipeline that is a pipeline of a typical retrieval augmented generation system, where we add some components that allow us to investigate our research question. And so we have at the beginning a retrieval system that receives queries and extract from the knowledge base a set of passages that are possibly relevant for answering this query. These passages are then processed and cleaned with standard NLP tools for making co-reference resolution and splitting the documents that are longer in short sentences that are then analyzed by another LLM to understand which are the most relevant sentences for answering the query. And so we have this part with top case selection, and we start from a set of sentences. And at this point, we have a representation of this sentence in the latent space that is obtained by exploiting the B-encoder model that performed the retrieval. And we perform a clustering of these sentences on the basis of their semantic. And so we build a set of clusters that represent the different aspect and the different content of the document, of the sentences that are retrieved from the knowledge base. What we are going to understand with our research question is if, given this context to the LLM for response generation in a specific order, can impact the quality of the response. In the sense that we want to understand if the order, we know from previous studies that there is some positional bias. Here we want to do a step forward to understand what is the best way of providing the knowledge, the contextual knowledge to the retrieval augmented generation system. If there is a difference in different way of organizing the context provided to the LLM for answer generation. Anyway, given this research question, we need also to understand which could be a way for assessing the quality of the response, in the sense that we provide the LLM with a set of sentences organized, ordered in different way, and for each different order in which the sentences are given an input to the LLM, we obtain a different answer, possibly a different answer. And we need to understand which is the best one. If we can understand and assess which is the best answer from the set that are generated by the same LLM model for the same query based on different ordering of the document, we can understand if there are some patterns, some regularity that allow us to understand that a specific order is the best and provide us most effective answer. Anyway, what we did to assess which is the best answer among a different set of answers provided by the LLM on the basis of the same query, we used another LLM that is fine-tuned for a ranking task, in the sense that we, given the sentences, we organize it according to different ordering and given an input to the LLM for response generation. We obtain, for example, 4 responses for the same query, the R1, R2, R3, R4 that you see in the plot. And we want to understand which among these sentences is the best for answering the query. what we do is providing asking to a large language module to assess which are the query and to rank in this query R1, R2, R3, R4 on the basis of their effectiveness, of their quality for the original query from the user. We know, however, that LLM suffer of positional bias, and so to perform this experiment is not needed only to provide the LLM these queries, but also to try to permute this query in different order to avoid the positional effect of that bias that has been proven for LLM models. And so at the end, we ask the model which is the best, we aggregate the result of the permutation, and we understand on the average which is the best ordering that improve the quality of the response returned by the retrieval augmented generation system. Okay, the main finding of our research is that the best way of ordering the cluster that include the documents that optimize the self-similarity are using sorting the class in descending order of similarity with respect to the query. Thus, the best order is selecting making the cluster and including the document in each of the cluster by descending similarity with the encoding of the query. This is the way of that improve the quality of the answer. On the opposite, the worst case was that we documented with our experiment was including the cluster in ascending from the lowest to highest order similarity with the opposite of the best strategy. We have also another variable that is the way in which the sentences are ordered within the same cluster. And in this case, we tried with our experiment to show that the best way of including the sentence is by aggregation order given by the hierarchical clustering that we use it for performing clustering. And so we compare this our best strategy that resulted from our experiment with other baseline strategies that are commonly used with retrieval augmented generation system. The one, for example, we have in this table 4 competitors. In one case, we provided directly the retrieval passages to the LLM, so we avoid all the intermediate cleaning that we described before. And instead, in the 3 central methods are random sentence ordering, sentence order by re-rank score, and sentence ordering by visiting order. And in each cell of this matrix, we have the number of times that a given strategy in the column was superior, resulted to be superior to the one on the row. And in the middle number, we have the number of ties, and then in the third number, we have the number of losses. For example, in the cases of the topmost right side cell, where we compare our best clustering strategy with strategy A, that is directly used as a retrieval passage, we have that our strategies was better in 66 cases, was as well as the other in 2 cases, and was worse in 43 cases. At the end, we aggregate all the cases and we perform some statistical significance test, and we conclude that our way of placing the context in the prompt of the LLM is superior to the other competitor. And so these are the final considerations of this first part of the talk. And the final consideration is that we proved that the quality of the responses generated by the LLM is drastically affected by the order of retrieved information within this prompt, and that providing the information in the prompt using a well structured way as we do can improve of over 34% over a system where the sentences are included in a random order in the prompt. This allows us to understand that coherent, fluent, and well-structured texts are critical for communication, not only of humans, but also to LLM. And so it is better to communicate to LLM in a well-structured way, as we did in our experiment. Of course, this is a preliminary experiment, and the paper will have some follow-up, hopefully. And in our case, the experimental evaluation is limited, and we use only conversational data set, and the future work will involve understanding if this characteristic is common also to other kind of task of retrieval task, and if other, for example, question answer can take advantage from clusterization as conversational search does. And so maybe we can have a 5-minute break, or
Oh, yeah. Why not?
so if you have some questions and curiosity about this part of the document, and we will have a second part that is more machine learning oriented than this previous one that was at least related to generative AI. And so if you have a question, that will be super happy to answer.
What I can do, Perego, is to break the recording into recordings.
Sure.
Okay.